Everybody, this is an underdetermined system of equations, meaning that we have more unknowns than equations. Now, that may not be the precise definition of underdetermined. That's how I'm using it here. Again, we have 4 unknowns, but only 2 equations. Now, another way to rewrite this bottom equation equivalently is like this. It's a z. I'm going to make this z with a little slash in a minute, not so we won't confuse it with 2. Okay, so in other words, I just subtracted z from both sides, and I could do something similar up here. Now you're going to see where we're going here. We're going to use something called the Cauchy Schwarz. We're trying to find upper bounds for all the variables. I chose z arbitrarily, but the symmetry of this pair of equations means that the math we use would be like finding the upper bound for all 4 of the variables, because this is symmetric in the sense we could relabel everything. That's not going to change the mathematics that we'll be employing here. Okay, now this is the very well-known Cauchy Schwarz inequality, and this is a lot of you guys who do linear algebra. This is called an inner product. This is the square of the magnitudes on the right-hand side, but you don't have to think about linear algebra in order to understand how to use the Cauchy Schwarz inequality. Now, we're going to use this top version here, and you're going to see why we wrote this down. If you come down here, notice that for our circumstance here, the way I'm using it, n would just be equal to 3. Okay, even though there's 4 variables up here, we're going to use the n equals 3 version of it, and you're going to see how that goes. Notice here they use a sub i's and b sub i's to connote real numbers. So right here, the w would be behaving exactly like a sub 1, and 1 itself would be behaving like b sub 1. And all the way across here, using subscripted notation, x would be the same as a sub 2 in the equation, in that statement of the Cauchy Schwarz. B sub 2 right here. And then finally, y would be a sub 3. And again, we're using 1 for b sub 3. Okay, again, folks, and if I didn't make any sense there, I'm right here. Okay, for n equals 3. So you see we have the square. The square you see right here is exactly the same as the square that's in this statement right here, this nice summation statement of the Cauchy Schwarz. And then all of this stuff over here, the stuff on the right-hand side of the inequality is exactly this. It's the sum of the a sub i's squared, which is what this is. If you take a look at your a sub i's, a sub 1 is w, a sub 2 is x, a sub 3 is y. And that's what we have right here is w squared plus y squared plus z squared, which corresponds to this first summation notation right here. Okay. Now this is called the one trick. There's a famous mathematician up at Harvard that calls this the one trick. Notice that the a sub i's and the b sub i's are all real numbers, and we can arbitrarily choose 1 here, because it's for all real numbers. There's no constraints there's no type of constraints on the real numbers that you're using. Okay, so you see, if you carry on like in this fashion, we have 1 squared plus 1 squared plus 1 squared. Well, that's the 3 you see right here. And y'all, again, it may be superfluous to put the 1s here, but I just wanted to make sure you saw how we're using the Cauchy Schwarz. Okay, a lot of people will leave the 1s out because obviously it's the multiplicative identity, but it helps you see what all the assignments are for this first rendition of the Cauchy Schwarz. All right, now if you continue on here, this is where we use this fact right here. W plus x plus y is equal to 42 minus z. Well, that's exactly what we replaced it. From here to here, we replace w plus x plus y with 42 minus z. And in a similar fashion, we have, let's see, I may have left something out here. No, we're good. 3, this 3 is this 3 right here. And then 588, that's 42 squared is 1764, not a hard calculation, right? And then 3 times 58 turns out to be 1764 also, okay? But again, right up here, you would have had 588 minus z squared is equal to w squared plus x squared plus y squared, which is what you see right here, okay? Now, a lot of things cancel out nicely here. The 1764 is present on both sides. 3 times 588 is 1764. What else cancels? The z-squareds. The z-squareds don't cancel, right? But anyway, when you expand this out, you do get all of this stuff here. And then the 1764s do cancel. If you divide through by 4 and factor out a z, you get this statement right here. Okay? Now, this certainly implies that z has to be less than or equal to 21. And that's fairly clear. Right, folks? If z were greater than 21, you would have a positive times a positive, right? Which would be positive, and this is less than or equal to 0, right? So z is definitely got to be less than or equal to 21 right here. So that would be our upper bound. Okay, that would be our upper bound. And notice, it wouldn't be the upper bound for z only. This is our upper bound. Let me call it UB. Upper bound. Which could be of some assistance. You would know nothing bigger than this number could be a solution to the equation. Now, you still might not be able to figure out any of the solutions really, but you'll know that none of the solutions can be bigger than 21. And now this is an integer, but this would apply for all real numbers, meaning you're going to have some non-integer solutions to this. I'm certain. I'm not that I know any, but we just know that the upper bound. So what we really have learned here is that W, X, Y, and Z are all less than or equal to 21. And folks, again, the way I worded this, perhaps it's suspicious. I said an upper bound for Z. I could have made the instructions find an upper bound for all the variables in the system, okay? And this would be the answer. I just said find it for Z, just because you have to pick one and work it, but again, you could have picked any of them, and the mathematics would have been similar, right? Very, very similar, just different names for the variables, So anyway, that does it. Cauchy Schwarz got the job done for us. Hope you enjoyed.